Hello everyone, welcome to MK Academic Solutions. So in this video I am going to explain about the ionic equilibrium. This is the lecture number 2. Okay, already I completed lecture number 1. So this is a continuation of that lecture. So in this video I am going to explain about the degree of dissociation, dissociation constant of weak acid and weak base, and Ostwald dilution law, ionic product of water. Okay. So now let us see one by one. First, we will go through ionization of acids and bases. We know acids and bases contain H plus ions, bases contain OH minus ions according to Arrhenius theory. So here we are going to consider Arrhenius theory. So acids and bases contain polar or ionic type of bonds. Hence they dissolve in the water, they get ionized and get ionized into protons and anions or hydroxyl ions and cations. Protons and anions in case of acid. In case of base, we can take hydroxyl ions and cations. Okay. So here, when you take the ionic compound, if you take the ionic compound, that process is called dissociation. When you take the polar compound, that process is called ionization. For example, HCl is there. HCl is a polar compound. So HCl dissociate as H plus Cl minus. This process is known as what? Ionization, and dissociation is completely for ionic compounds. However, both we are going to consider same only. Ionization or dissociation we can consider same only. Okay, right. So for dissociation, for example, you take the NaOH, sodium hydroxide. It is completely ionic compound. Dissociate as Na plus OH minus Na plus OH minus ions. Okay. That is the meaning of ionization and dissociation. Dissociation and ionization. Next, let us see the strong acid and weak acid, or strong electrolyte and weak electrolyte. So, what is a strong electrolyte and weak electrolyte? So, strong electrolyte means the extent of ionization is more. Extent of ionization is more or large. They are called strong acids and strong bases, strong electrolytes. As they conduct the electricity, we can also call them as the electrolytes. Okay, for example, you take HCl is a strong electrolyte, H2SO4 is a strong electrolyte, and sodium hydroxide is a strong electrolyte. Okay, next, weak electrolytes means the percentage of dissociation is very less. So the extent of ionization is very less. They are called weak substances. For example, you take the organic acids such as acetic acid, malic acid, and bases such as ammonium hydroxide, etc. So the extent of ionization is less means that is called weak acid. The extent of ionization is more, that is called strong acid or strong electrolyte. So here both acids and bases you can consider them as the electrolytes. Okay. Next let's see ionization constant of acid. So what is the ionization constant of acid? For example, generally we are going to take a HCl. HCl is the acid. This HCl is going to dissociate as H plus A minus. So this is is the dissociation of acid. So now here dissociation constant Ka. Okay, let us consider this as the reversible one. Ka is equal to concentration of H plus ion and A minus ion by He. So this is the dissociation constant of acid. Okay. So here Ka is called what? Dissociation constant of acid. Same like how we write the law of mass action. The same manner we are going to write. Instead of Kc, what we are going to take here? Ka we are going to take. Okay. So here Ka represent what? Dissociation constant of acid. Ka is what? Dissociation constant of acid. Dissociation constant. Dissociation constant of acid. Okay. See here, Ka increases. Strength of acid is also increases. Strength of acid also increases. Strength of acid also increases. Means K is the direct measure of strength of acid. Okay. Next, so let us consider here. I am going to take A, B, C, and D. A, B, C, and D. So out of this A, B, C, D, and all are the acids only. It is having Ka values to take 1 into 10 to the power of minus 2. Here 1 into 10 to the power of minus 3. This one 1 into 10 to the power of minus 4. For this 1 into 10 to the power of minus 5. So now which is having a more Ka value, that is only the strong acid. See here, A is having more Ka value, D is having very less Ka value. So strength of acid A is greater than, B is greater than, C is greater than D. Means Ka increases, strength of acid is also increases. Next, let us see. Ionization constant of base. For example, general base you take MOH. MOH general base we are going to take. So here MOH is gives rise. Okay. Alright. So here MOH gives rise as M plus OH minus ions. M plus and OH minus ions. So now here dissociation constant of Kb. Kb is equal to simply M plus concentration of M plus and concentration of OH minus ions by MOH, concentration of MOH. Okay, this is the Kb. Here also what we are going to do, we are applying the law of mass action and we are writing the Kb. Instead of Kc, what we are writing Kb. So here what is the Kb means dissociation constant of base. So here Kb is dissociation constant. Dissociation constant of base. Okay, dissociation constant of base. So now here Kb is also what? Kb is direct measure of strength of base. Kb is what? Direct measure of strength of base. If Kb value increases, strength of base is also going to be increases. So Kb is a direct measure of strength of base. Strength of base. Direct measure of strength of base. Okay. So here Kb increases, strength of base also increases. Strength of base is also increases. Okay, right. See, for example, here also take one example. Let us consider A, B, C are the bases. So for them, dissociation constant Kb is 10 to the power of 10 square you consider, 10 to the power of 3 you consider, 10 to the power of 10 you consider, or simply consider 10. 10 you consider. So out of these three, which is the strong base and which is the weak base? Out of these three, strong base is what to be? B is the strong base. B is strong base. B is the strong base. Whereas C is the weak base. Why? Because here B is having more Kb value, whereas C is having less Kb value. Okay, this is about ionization constant of base. Okay, next see Ostwald dilution law. So now what is the Ostwald dilution law? See here, Ostwald applied the law of mass action. So what is the law of mass action? You know, apply the law of mass action to the ionic equilibrium of weak electrolytes, and derived an equation which is known as Ostwald dilution equation. And according to this Ostwald dilution law, the degree of dissociation of electrolyte is directly proportional to the square root of the value or inversely proportional to the square root of concentration. So what is the Ostwald dilution law is telling? So the degree of dissociation of an electrolyte, or simply the extent of ionization of an electrolyte, is directly proportional to the square root of volume. Means volume of the vessel increases, degree of dissociation is also increases, and concentration increases, degree of dissociation is going to be decrease. So here, so what is the degree of dissociation? So degree of dissociation. Here we are having the degree of dissociation. Degree of dissociation indicated with alpha. Degree of dissociation indicated with alpha. Alpha is what? Degree of dissociation. Degree of dissociation. Okay. Alpha is the degree of dissociation. In short, we can call it as the DOD, degree of dissociation. See here, degree of dissociation alpha is equal to number of particles dissociated. Number of particles or molecules, number of particles dissociated by total number of particles. Total number of particles. That is called alpha, degree of dissociation. Or some percentage of degree of dissociation means percentage. Sometimes they will give you percentage of degree of dissociation. Percentage of degree of dissociation means number of particles dissociated by total number of particles. Total number of particles into 100%. Percent means per 100 how many molecules are dissociated. That is nothing but percentage of degree of dissociation. Okay. Now what are the factors which influence on the degree of dissociation? Okay. factors. Factors, when you see the factors effect on factors effect on DOD, degree of dissociation alpha. Okay, degree of dissociation alpha. The first one is nature of electrolyte. Nature of electrolyte. Nature of electrolyte. If the electrolyte is strong, so here acids and bases both are called what? Electrolytes. Why? Because they conduct the electricity. Okay, that point we keep in mind. So nature of electrolyte. If electrolyte is strong electrolytes, more alpha. Strong electrolytes, more alpha, means more degree of dissociation. Weak electrolytes, less alpha, less degree of dissociation. Next, concentration, you know, alpha is inversely proportional to square root of concentration. This is the DOD, degree of dissociation, is inversely proportional to square root of concentration. So DOD, degree of dissociation, is inversely proportional to alpha, is inversely proportional to square root of concentration. Means here concentration increases, degree of dissociation decreases. Next, volume increases. DOD, degree of dissociation, is directly proportional to square root of volume. Volume increases, degree of dissociation is also increases. Next, nature of solvent. See here, nature of solvent also effect on the degree of dissociation. The same type of substance, if you change the solvent, the extent of dissociation is also going to be changed. Nature of solvent, see here. So nature of solvent, we can take one factor, that is dielectric constant. Nature of this, the solvent is having dielectric constant, more dielectric constant. If solvent is having more dielectric constant, what is the dielectric constant? Means the ability of the solvent to dissociate the compound into ions. That is called dielectric constant. Means simply remember, solvent can divide the compound into ions. That ability, that property is called what? Dielectric constant. See here, more dielectric constant, more alpha, more degree of dissociation. Here alpha is nothing but degree of dissociation. Less dielectric constant, less alpha, less dielectric constant, less dielectric constant, less alpha. Next, temperature. See here, temperature is directly proportional to alpha or degree of dissociation. Temperature is directly proportional to what? Degree of dissociation. Temperature increases, degree of dissociation is also increases. So these are the factors which affect on the degree of dissociation. Okay, now we know what is the degree of dissociation and what are the factors which influence on the degree of dissociation. Next, let us see. So now we are discussing about what? Ostwald dilution law, right children? So according to this Ostwald dilution law, the degree of dissociation. Now we know what is the degree of dissociation of electrolyte is directly proportional to the square root of concentration or square root of concentration. So directly proportional to the square root of volume and inversely proportional to the square root of concentration. So now how we can prove this? How we can prove this? So now let us take one acid. Okay. Now let us take one acid here. For example, HA. We are going to take HA is going to dissociate as H plus and A minus. So this is the general acid here we are going to take. Okay. So now here we know at initial concentration. Initial concentration. Initial. At initial. Okay. Initial. Initial concentration. Initial concentration is C. Initial concentration is C. 0 and 0. At equilibrium. At equilibrium. At equilibrium, C minus C alpha, and it is going to form C alpha. It is going to form as the C alpha concentration. Okay, right now for this Ka, how will write Ka? Concentration of H plus ion by into concentration of A minus by concentration of HA at equilibrium. Okay, right now here Ka is equal to what is the concentration of H plus ion? C alpha at equilibrium into concentration of A minus, that is also C alpha. Concentration of HA, what is the concentration of HA? C minus C alpha. C minus C alpha. So now here Ka is equal to C into C square into alpha square by, so here C you take common, C if you take common means 1 minus alpha. 1 minus alpha you will get. So here C square and C will get cancelled out. So here Ka is equal to C alpha square by 1 minus alpha. See here 1 minus alpha is nearly equal to 1 only. Why? Because alpha is very less for the weak acids. Alpha is very less. Alpha is very less for weak electrolytes. Weak electrolytes. Okay. Alpha is very less for the weak electrolytes. Therefore, Ka is equal to C alpha square by 1, or simply you can take as K is equal to C alpha square. So now here Ka by C is equal to alpha square. Okay, therefore what we can write? So now here K is what? A dissociation constant of acid. So just to remove the dissociation constant of acid, when you remove the constant value, equal become proportional. Therefore, alpha square is proportional to 1 by C, or alpha is proportional to square root of 1 by C. Okay. So in this way we can prove that the degree of dissociation here. What is the alpha? Alpha is nothing but the degree of dissociation is inversely proportional to 1 by square root of C. So here for binary, you simply take it is for binary. Okay. Next, let us take with volume. Concentration. We know alpha is proportional to 1 by square root of C. And now let us take with volume. So the same acid I am going to take. Okay. Same binary acid I am going to take. HA is gives rise to H plus A minus, right? Initial how many moles? 1 mole I am going to take. Initial moles. Here I am not going to take concentration. Initial moles I am going to take 1 mole, and it is 0 mole and it is also 0 mole. Next, at equilibrium, 1 minus alpha and alpha, this is also alpha. So this is what number of moles. This is what number of moles. So now number of moles, how we can convert into concentration? So what is the which concentration here we are going to take? Molarity concentration we are going to take. So molarity is equal to number of moles by volume in liter. So now we are having number of moles at equilibrium. Number of moles. Okay. Initial moles at equilibrium. Number of moles 1 minus alpha and alpha. Okay. So therefore, for this, Ka is equal to H plus ion concentration and A minus ion concentration by HA concentration. Okay. So here concentration means molarity we should take, but here we are having number of moles. So simply number of moles by volume in liter. Okay. Alpha by V into alpha by V by 1 minus alpha by V. So here number of moles by volume in liter, that is the concentration. Okay. Therefore, now Ka is equal to, how I can write here, alpha into alpha square by V square into V by 1 minus alpha. Like that I can write. So now here Ka is equal to, so now here V and V square will get cancelled out. So now what is the remaining here? Alpha square by V into 1 minus alpha. So here we know 1 minus alpha is nearly equal to 1. Why? Because alpha is very less than the 1. Alpha is very less than the 1. Okay. So means alpha is having negligible value here. So that's why 1 minus alpha, what we are going to consider? 1 only we are going to consider. Therefore, Ka is equal to alpha square by V. Therefore, Ka into V is equal to alpha square. Therefore, alpha is equal to square root of Ka into V. So, this is the relation, or simply if you remove the constant means square root of V proportional to alpha, that is degree of dissociation. Means degree of dissociation is directly proportional to square root of V. Means value increases, alpha is also increases. Means the degree of dissociation is also increases. Okay. Next, let us do. Okay. Next, so now here we are having mono basic means binary electrolytes we are having. Binary electrolyte means one cation and one anion only is there. If any more cations and more anions are present, how we can do? How we can find out? For example, HCl. HCl directly we use the Ka value. Why? Because it is the binary. So here dissociation is single step only. Here dissociation is what? Dissociation is single step. Okay. So therefore here HCl dissociates as H plus Cl minus. H plus and Cl minus. So for this directly Ka we are going to calculate as H plus ion concentration, Cl minus ion concentration by He. Okay, like that HCl, not HCl, HCl. HCl. Okay, right? So now, if we are having polybasic acids, polybasic acids means, for example, H2SO4 is there, H3PO4 is there, okay, etc. etc. So for this, how we are going to find out the dissociation constant? Here, in case of H3PO4, you take H3PO4. Here, dissociation is what? Not a single step; it takes in the multiple step. Here, dissociation is multiple step. Dissociation is multiple steps. Dissociation is in what? Multiple steps. So here H3PO4. So the H3PO4 gives rise to H2PO4 minus 1 plus H plus. For this we are going to consider Ka1 and H2PO4 minus 1 gives rise to HPO4 minus 2 plus H plus. For this we are going to consider it as the Ka2. Next, HPO4 minus 2 gives rise to PO4 minus 3 plus H plus. So this is the Ka3. And overall reaction, overall dissociation, how is the overall dissociation? Overall H3PO4 gives rise to 3H plus PO4 minus 3. So for this dissociation constant, consider Ka. For this type, here Ka is equal to, for this type, Ka is equal to Ka1 into Ka2 into Ka3. So this already I taught you in the chemical equilibrium only. Okay. So if you get any overall reaction, overall reversible reaction by addition of one or more reactions, the dissociation constant or the equilibrium constant of the overall reaction is the product of equilibrium constants of added reactions, which means simply, see here we are getting this resultant reaction. How we are getting this resultant reaction? By adding 1, 2 and 3. So the equilibrium constant of this resultant reaction is equal to the product of these three equilibriums. Okay, that is Ka is equal to Ka1 into Ka2 into Ka3. Okay, so this is next. Let us see an example here. The dissociation constant of acetic acid is 1.8 into 10 to the power of minus 5. So means Ka they have given Ka is equal to 1.8 into 10 to the power of minus 5, and temperature 298 Kelvin they have given. Okay, means constant temperature they have given. Calculate the degree of dissociation. We need to calculate the DOD. What is the DOD? Okay, concentration they have given. Concentration how much they have given? 0.1 molar solution they have given. Okay, now concentration directly you take what is 0.1 molar. So now here acetic acid. How the acetic acid is going to dissociate? Acetic acid CH3COOH gives rise to CH3COO minus plus H plus. Okay, so at equilibrium only, at equilibrium directly they have given equilibrium concentration. So what is the equilibrium concentration? 0.1 molar is the concentration. Okay, na? So I simply just write for this. I will write here. It is C. Initial concentration you take like this. C initial C 0 and 0, C minus C alpha, and here it is the C alpha, it is the C alpha. Initial equilibrium equilibrium. For equilibrium, C into C minus C alpha and C alpha. So here Ka is equal to, we know, C alpha into C alpha by 1 minus C minus C alpha. So here Ka is equal to C square alpha square. C I am going to take common 1 minus alpha. So here Ka is equal to what? C will get cancelled out. C alpha square by 1 minus alpha. So here 1 minus alpha we are going to consider negligible. Why? Because it is acetic acid, a very weak acid. So therefore Ka is equal to C alpha square. Therefore alpha square is equal to Ka by C. Ka by C. So now therefore alpha is equal to square root of Ka by C. Alpha is equal to square root of Ka by C. Okay. So here square root of Ka by C is equal to alpha. Okay. So therefore alpha is equal to square root of 1.8 into 10 to the power of minus 5 by 0.1. Okay. So now this I can write as a square root of 1.8 into 10 to the power of minus 4 0.1. Okay, 10 to the power of minus 4. I can write. Simply it is 10 power minus 1 goes to numerator, 10 power plus 1, 10 power plus 1, 10 power minus 1, 10 power minus 4. So alpha is equal to, so here square root of 1.8 into 10 power minus 2. Here this is the alpha. Okay, right. This is the answer for that. Next let us see. Calculate the concentration of OH minus ions in 0.1 molar solution of ammonia. So ammonia NH3 plus H2O is gives rise to NH4 plus OH minus. Okay. So here it is also what the binary electrolyte. So for this here Kb, how I can write Kb is equal to Kb is equal to C alpha square. Simply what you consider Kb is equal to what here C alpha square. Therefore alpha square is equal to square root of Kb by C. Square the same manner. How I have derived the same manner we can derive. Okay, right? So now here what is the Kb? 1.76 into 10 to the power of minus 5 by C. What is the concentration? 0.1 molar by that is equal to alpha. Okay. So here alpha square we are taking alpha. Here. So here alpha square not here. So here alpha is equal to, okay. So the alpha is equal to, this is the value. So now if you can solve this, you will get the answer for this. Okay. Right. Next, experimental verification of Ostwald dilution law. So how we can verify the Ostwald dilution law? See here. How we can verify? So here alpha is equal to lambda v by lambda infinite. So here by using the Cole-Roche law, we can use the Cole-Roche law. So here what is the alpha? Alpha is what? degree of dissociation. Degree of dissociation lambda v by lambda infinite. This is infinite. Okay. So here lambda v is equal to conductivity, equivalent conductivity at a given dilution, conductivity at a given dilution, lambda infinite, conductivity at infinite dilution. So lambda infinite is the conductivity at infinite dilution. Okay. So by taking these three values, conductivity experiments, we can get these values and we can find out the alpha, and alpha value we find at different dilutions, and we substitute the value and substitute value in alpha is equal to square root of Ka by C, or alpha is equal to square root of Ka into B. So in these two equations we are going to substitute, and if you get a constant Ka value, means Ostwald dilution law is verified. If you not getting constant value, means Ostwald dilution law is wrong. But here we get the constant Ka value for the weak electrolytes, so that Ostwald dilution law we can prove in this manner. Okay, right. So this about this we can learn in the electrochemistry. Just simply remember how we are going to verify. Okay. Next, limitations of Ostwald dilutions law. What are the limitations of Ostwald dilution law? So applicable for only dilute solutions of weak electrolytes. So when you take a strong electrolytes, it is not at all going to applicable, but it is applicable for only weak electrolytes. Not applicable for strong electrolytes, and not applicable for concentrated solutions. Means we need to take the only dilute solutions. Applicable. Concentrated solutions we are going to take, means they are not at all going to dissociate. We cannot apply. Means first one is applicable for weak electrolytes. That will be dilute. But when you take the concentrated solutions, not at all going to apply. Next, importance of Ostwald dilution law. Used to calculate K, dissociation constant, when we know the degree of dissociation, and used to calculate degree of dissociation alpha when we know the dissociation constant. Okay, these are the importances of Ostwald dilutions. Next, let us see factors. These factors I have explained you already. Next, ionization constant of water. What is the ionization constant of water? So the product of H plus ions and OH minus ions present in the water is called what? Ionization constant. So the product of H plus ions and OH minus ions is called ionic product, or the product of H3O plus and OH minus ions in the water. That is called what? Ionic product of water. Ionic product of water indicated with Kw. Okay. See, we are going to take H2O. So this H2O dissociate as H plus plus OH minus. So for this K dissociation constant, how we are going to write, means equilibrium constant, how we are going to write, simply just remember how we are going to write the equilibrium constant. H plus into OH minus by H2O. H plus and OH minus by H2O. Like this we are going to write. Okay. So now you send this H2O this side. K into H2O, that is equal to H plus ion concentration into OH minus ion concentration. So this total term we can write as the KW. KW is equal to H plus ion concentration into OH minus ion concentration. Or we can take one more type also. You take H2O plus H2O is gives rise to H3O plus OH minus ion. Here also we are going to write the K will write equilibrium constant, we will write K. Equilibrium constant K is equal to H3O plus concentration of H3O plus and concentration of OH minus ions by concentration of H2O square. Concentration of H2O square, like this we will write. And here K into concentration of H2O square is equal to H3O plus concentration into OH minus ion concentration. Okay. So this total term what we are going to consider now, KW. Okay. KW is equal to H3O plus concentration into OH minus ion concentration. Means this is also the dissociation constant of water, and this also we can consider as water dissociation constant of water. Okay. There is no difference between them. So generally H plus cannot exist independently in the water. It always exists as the H3O plus. That's why we are going to take this one, and this is also correct. Okay. This is the ionization constant of water. So what is the ionization constant of water? Means the product of H plus ions and OH minus ions, or the product of H3O plus and OH minus ions in the water. Okay. If see, if we are going to take, if we take only water, here H plus ion concentration is equal to OH minus ion concentration. H plus ion concentration is equal to OH minus ion concentration. This is the neutral. It is what? Neutral. And so what is the KW? Neutral. That later is. Okay. If H plus, if we add acid, if we add acid, H plus ion concentration is greater than OH minus ion concentration. If we add base, H plus ion concentration is less than the OH minus ion concentration. If we add base, okay. So neutral H plus ion concentration is equal to OH minus ion concentration. If you add acid, more H plus ion concentration will be. If you add base, more concentration of OH minus ions, less concentration of H plus ions will be present in the water. Okay. So now here Kw for neutral, Kw for Kw depends on temperature also. Kw depends on temperature, depends on temperature. So here at 0 degree Celsius, at 0 degree Celsius, Kw 10 to the power of minus 14. At 60 degree Celsius, Kw is equal to 10 to the power of minus 30. Means here temperature increases, ionic product means ionic product of water is also increases. So here temperature increases, ionic product of water is also increases, means ionic product of water depends on water temperature increases, ionic product of water is also increases. Okay, next let us find the concentration of solution. Find the concentration of solution. Concentration of the solution of H3O plus and OH minus ion for a solution of weak acid and weak acid HA whose Ka value is 2 into 10 to the power of minus 8 and 8 moles of acid is taken. Okay, so here what is the given data? What is the given data here? We need to find the what is the H3O plus ion concentration and what is the OH minus ion concentration. Okay, and here Ka they have given, Ka is equal to 2 into 10 to the power of minus 8 they have given, and number of moles they have given, number of moles how much they have given? 8 moles. What is the volume they have given? Volume they have not given, means volume you take 1 liter. Okay, so they are not mentioned the value, means compulsory what is the value, you take the 1 liter only. Okay, therefore here HA dissociated as H plus A minus. HA dissociated as what? H plus A minus. Okay, so here initial concentration is 8 and 0 8 minus 8 alpha. Directly I am going to take the concentration 8 moles per liter means 8 molar. Okay, and here it is 8 alpha and it is also 8 alpha. This is the initial and it is at equilibrium. Okay, so now here Ka is equal to 8 alpha into 8 alpha by 8 into 8 minus 8 alpha, 8 minus 8 alpha. Therefore K is equal to 8 square into alpha square by 8 minus alpha, 8 into 1 minus alpha. Here 1 minus alpha is negligible. Here K is equal to 8 square will get cancelled out and 8 alpha square will be okay, right. So now here Ka by 8 that is equal to alpha. Ka by 8 is equal to alpha square. So therefore alpha square is equal to how much? Ka they have given 2 into 10 to the power of minus 8 and 8 concentration, see 8. So therefore alpha square is equal to 2 ones are 2 4s are means 1 by 4 means 0.25. 1 by 4. Okay, 0.25. 0.25 into 10 to the power of minus 8. Okay. So therefore alpha is equal to square root of 0.25 0.25 into 10 to the power of minus 8. Or else alpha is equal to square root of 25 into 10 to the power of minus 10. Therefore alpha is equal to 5 into 10 to the power of minus 5. This is the alpha value. So when you know the alpha value, so here what is the concentration of H plus ion? 8 alpha. So concentration of H plus ions is what? 8 alpha. 8 alpha. So therefore 8 into 5 into 10 to the power of minus 5. This is the concentration of H plus ions. Okay. Right. Concentration of H plus ions. So what is the value we get here? 8 5 is 40 into 10 to the power of minus 5. This is the concentration of H plus ions, or simply 4 into 10 to the power of minus 4 is the concentration of H plus ions. And what is the concentration of OH minus ions? Here we know Kw is equal to H plus ion concentration into OH minus ion concentration at 298 Kelvin. It is 10 to the power of minus 14. 10 to the power of minus 14. That is equal to H plus ion concentration 4 into 10 to the power of minus 4 into OH minus ion concentration. Therefore 10 to the power of minus 14 by 4 into 10 to the power of minus 4, that is equal to OH minus ion concentration. Okay. So now 10 to the power of 4, 10 to the power of minus 10 by 4, 10 to the power of minus 10 by 4 means what we can write here? 0.25 into 10 to the power of minus 10, that is the OH minus ion concentration. Okay. So now this how we can write here? 2.5 into 10 to the power of minus 11, that is the OH minus ion concentration. So in this way we can find the H plus ion concentration and the OH minus ion concentration. Okay, right. So this is the question. Okay, right. Question and answer. Okay. H plus ion concentration we got means H plus means H3O plus, directly H plus or H3O plus, both are same only, and OH minus ion concentration both we got. Okay. Next okay, right. So with this I am going to end this video. So what we have discussed in this video, let's see what we have discussed here. What I have explained here. So first of all, I welcome you to our channel, that is MK Academic Solutions. And then after, what is ionization? What is the ionization of acids and bases? And what is dissociation? What is ionization? And the next, strong acid, strong electrolyte and weak electrolyte, based on the extent of dissociation, ionization. Ionization constant, how to write the ionization constant? Based on the ionization constant, Ka values. K is direct measure of K is the dissociation constant of acid. Dissociation constant of acid increases, Ka acidic strength also increases. Next, ionization constant of base. This is the ionization constant of base. Means Kb increases, strength of base is also going to be increased. How it is I shown you. And next, Ostwald dilution law. What is the Ostwald dilution law? So application of law of mass action for the weak electrolytes, that is the Ostwald dilution law. And here degree of dissociation is directly proportional to the square root of value, and degree of dissociation inversely proportional to the square root of concentration for binary electrolytes. Okay, this is applicable for the binary electrolytes. And then after, what is the degree of dissociation I have explained you, and what are the factors which affect on the degree of dissociation also explained you. And next, and degree calculation of dissociation constant and degree of dissociation for the acids and bases. I taught you how it is good. Means I proved here Ostwald dilution law. Next, with acids with value I proved. Next, dissociation constant for the binary means it is a single step. If it is we are going to take polyprotic acid, poly or polybasic acids we are going to take, means what is the dissociation constant I taught you. And next I explained you some few questions there to calculate the degree of dissociation. And next, here also one question to calculate the degree of dissociation. And the next, experimental verification. So this part you learn in the, actually in electrochemistry you learn. Okay, that is conductivity at a given dilution and conductivity at a infinite dilution. The ratio will be the alpha. Okay, and verification also. So we find the alpha in different dilutions and we substitute the alpha value here. And if you get the constant Ka, that is law is verified. Means Ostwald dilution law is verified. Next, limitations and importances of Ostwald dilutions law. And next, factors is already completed. Next, ionization constant of water. What is the ionization constant of water? So what are the conditions for the acids and bases? And one model problem on the acids and bases. Okay. Thank you for watching. We continue with our next videos.